So I decided that why not go right ahead and do the rest of this review sheet for those that would like to see all the answers written out and explained, since I had to make an answer key anyway. So let's do it. So starting the first problem, again, let me pull my pen up here. It says, fill in the blank with the words best that come to mind from what we've learned. And in so many words, obviously, it's not word for word translation. I'm doing the spirit of the instructions. But anyway, the first one says, examine the shape to the right. These shapes are, well, if you look at these shapes, they're evenly spread out. So these shapes are symmetrical or even. Therefore, these molecules are non-polar. The distribution of the electrons would be even. So therefore, if they're non-polar, they're only able to mix with solvents that are non-polar, with the phrase like dissolves like. These shapes down here show an uneven distribution of the atoms on the outside, which means there would be an uneven distribution of the electrons within the molecule. So these shapes are uneven or asymmetrical. So these molecules are polar, and they're able to dissolve in polar solvents. And water is polar, which means these would be able to dissolve in water. With that being said, since these are molecules, because molecules have shapes, where ionic compounds are just repeated crystal structures, so when these get dissolved, they get surrounded by water, but they do not get pulled apart. So the correct representation of that would be the state of matter, which we don't know, would just go to aqueous. So in this case, it would be this first one. If they told you it was a solid, it would be number 2, but they don't tell you that information. Question, we've been talking about molecules and ions, kind of, or ionic compounds. How do you classify it? Well, simply a molecule is all nonmetals, where an ionic compound contains something with a positive and something with a negative. So we know like NaCl would be ionic, something that would be molecular would be CH4. Alright, number 3, they say, write the complete ion equation for a reaction of sodium phosphate with magnesium nitrate. Okay, so I'm going to do the molecular first, because it's kind of hard to do the molecular without doing sorry. It's kind of hard to do the complete ionic without doing the molecular first. So I'm going to start over here. So I'm going to do sodium phosphate, so it's Na3PO4 aqueous, plus magnesium nitrate, so it's MgNO3 2, and that's going to give me NaNO3 plus Mg3PO4 2. That will be insoluble. That will be aqueous, aqueous, aqueous. So we have 2 nitrates, 3 phosphates. 2 phosphates, so we'll put 2 here, which gives me a 6 here, which gives me then a 3 here. Okay, so from that, I'm going to derive the complete. So now I'm going to get 6 sodium plus 2 phosphate plus 3 magnesium plus 6 nitrates, and that's going to give me 6 sodiums, 6 nitrates, and then it's going to give me the magnesium phosphate as a solid still. So there you go. There's your complete. And then your net, again, with our spectator ions, we got spectator, 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 so it's going to be 3 magnesium plus 2 phosphates. It's going to give me magnesium phosphate. If you know the solubility rules well enough, it is possible just to jump straight to this, and let me show you how I do that. potassium sulfide, aluminum nitrate. Okay, so the combinations that could form the precipitate are potassium nitrate. Well, no, because nitrate's always soluble. So there, the option then in this case is going to be Al, aluminum sulfide. So it's going to be Al2S3. So that is going to be our precipitate. So to write the net equation, we know there'll be 2 aluminum ions plus 3 sulfide ions are going to give you Al2S3 solid. So it is possible to go straight to the net. You just have to really think about it logically. So anyway, we did those earlier. Let's look at number 6. Says calculate the volume of a 0.45 molar NaCl solution that would contain 28.5 grams of sodium chloride. All right, well, what do they give us? They give us the molarity, which we know is 0.5 molarity, which means there are that many moles of NaCl per liters of solution. Okay, well, they're asking for the volume, so we're looking for liters. Now, they don't give us moles, but they give us the next best thing, which is grams. So I'm going to get 28.5 grams of NaCl. I'm going to multiply it by, I think it's 58, but I'll check. 23 plus 35.5. So it's going to be about 58 grams of NaCl in 1 mole. So I know 28.5 divided by 58. So that gives us 0.49 moles of NaCl. So now I can actually plug in numbers. So 0.45 equals 0.49 moles of NaCl over the liters. So it's really 0.49 divided by 0.45, and the answer is 1.09 liters. Okay, so with that being said, let's move on to the next one. It says a solution is made by 25 grams of sugar and 100 grams of water. Calculate the percent mass concentration. Okay, the percent mass concentration means the percent equals grams of solute over grams of solution. Okay, the grams of solute we know is 25.0 grams of sugar, which is C6H12O6 for your glucose, and the grams of solution. Now remember, solution is solute plus solvent. So really, this is 125 grams of solution. So the percent is just 25 divided by 125 times 100, and we get 20% NaCl solution. Okay. Moving right along. We did this earlier, and now we have another one. Let's do it. All right, step 1. Write out what we know. Okay, we know that it's going to be silver phosphate is the precipitate, and to balance this then I'm going to put a 3 here and a 3 here. Let's do our ions, so it's going to be 3Ag plus 3NO3 negative plus 3K plus PO4 negative 3. It's going to give you 3 silvers plus phosphate plus, oh, ha, no, you are not going to get that. That is when you go quickly. So this we know does not dissociate. And you're going to get 3 Ks and 3 nitrates. All right, start with initial concentrations. We've got 1.6 m equals moles of silver nitrate over 3 liters. So 1.6 times 3 gives us 4.8 moles of silver nitrate. That's a 1:1:1 ratio. So we've got 4.8 moles to begin with. We have 4.8 moles to begin with. It's a 1:1 ratio. Let's look for the potassium phosphate. We have 2.6 liters moles of potassium phosphate, and that's equal to 3m. So 2.6 times 3 gives us 7.8. So we have 7.8 moles of K3PO4. That's a 1:3 ratio. So 7.8 times 3 gives us 23.4 moles of K, and this gives us 7.8 moles of phosphate. Well, this is the initial conditions. We know that the amount of moles of potassium and nitrate won't change because they're spectator ions, so this still will be 23.4 moles. This still will be 4.8 moles. So to get the concentration of those ions at the end, we just have to do it by the new liters. So we're going to take the 23.4 moles of K plus, divide it by the 5.6 liters, and our K plus concentration will be 4.2 m of K plus. We do that now again for the nitrate, so we've got 4.8 moles of nitrate divided by 5.6 liters, and that gives us 4.8 divided by 5.6, 0.85 molarity of our nitrates. Okay, so not too hard. Now we know we have to look at the silver and the phosphate. Well, I'm going to look at silver. Silver is 4.8 moles. I know that I need 3 silver for every 1 phosphate. So 3 moles of silver for every mole of phosphate gives me 1.6 moles of phosphate. Well, that tells me that this is the limiting reagent, because the 4.8 will be consumed with the 1.6. Well, I have 7.8, so I have plenty of phosphate. Silver runs out, so the molarity of silver is 0. But I have 7.8 minus 1.6, so I'm left with 6.2 moles of phosphate in my now 5.6 liters of solution. So I do 6.2 divided by 5.6 gives me 1.1 molarity of phosphate. And there's your 4 ion concentrations. There's your phosphate, there's your silver, there's your potassium, and there's your nitrate. All right, there we go. Thank you.